Welcome to Boat Physics, where the natural laws are anti-capitalist. Here I present the argument that the ships in Pirates of the Caribbean are what I like to call supercrafts, and I will even provide Marvel and DC equivalents. The Flying Dutchman is a mix between Aquaman and Death, a punk rock version of the Grim Reaper from the Sandman comics. I include Death because the ship and the captain are one. He has to carve out his heart as part of the initiation rite, which doesn't make sense to me, because Davy Jones initially carved out his heart for reasons completely unrelated to his job. But all captains in this universe struggle with work-life balance, and cardial sacrifice has now become part of the job description. It's implied that it's the captain who gives the ship her power. When the captain isn't dicking around and growing tentacles out of his face, he's supposed to be ferrying people lost at sea to the next life. So where does Aquaman come into this? Quick question. What the fuck? Follow-up question. How the fuck? According to totally peer-reviewed sources like pirates.fandom.com, the Flying Dutchman is 175 feet long and weighs 420 pounds. Since Disney is American and the Caribbean was, at the time of filming, under forced imperial rule, we're going to assume that these are imperial tons. So the Dutchman weighs 426,740 kilograms. Using the highest tech 3D model from Sketchfab.com, I calculated that the Dutchman has a total volume of 6,704 cubic meters, with 5,851 cubic meters of empty space. When the ship is underwater, that is, presumably, full of water, especially given the state of the crew. So that is 6,143,498 kilograms of water, making the ship 6,570,238 kilograms total. That would require a force of 64,388,328 newtons to lift. Who's doing that lifting? Presumably the captain wishing really hard. But I have a different hypothesis. Like any God-fearing fish, the Flying Dutchman uses a swim bladder to rise and fall in the water column. Using electrolysis, a power any self-respecting, God-adjacent entity worth their salt possesses, water can be split into oxygen and hydrogen gas. Using this absolutely canon ability, the Dutchman can be filled 62.5% full of air and rise to the top with an acceleration of 1 meter per second squared. Once it has resurfaced and the bilge has been pumped, the ship has a buoyancy force of 3,733,974 newtons, displacing 381 cubic meters of water. Now let's look at the physics of the act of sailing. There are many forces at play on sailboats. There's the gravitational force of the boat, as well as the gravitational force of the sailors, who move around and affect the balance of the boat. This is nearly negligible on tall ships like the Dutchman. There is the force of the wind and the force of the sails, which is rarely going in the same direction. There is the force of water on the keel and the drag force of water on the rest of the hull. Drag is like friction, but for objects moving through fluids. The drag force is the product of the drag coefficient, the density of the fluid, the velocity of the object through the fluid, and the area of the object moving through the fluid. Drag force increases as the speed of the boat increases. This means that as the velocity of the boat increases, acceleration decreases. Those example values are from the Lady Washington, which we will discuss later. We covered the concept of lift at the beginning of the quarter, and how the angle of the wing causes an increase of pressure beneath it and a decrease of pressure above it, causing the wing to lift. With sailing, the wings are vertical. The sail cuts through the wind and curves in such a way that an increase of pressure is created at the back of the sail, and a decrease in pressure forms at the front of the sail. So the sail, and thus the boat, is pushed and pulled forward in the leeward direction. While this occurs, the wind also pushes the sailboat over towards the horizontal. That's where the keel, or centerboard, comes in. As the boat is rotated around the heeling moment, the keel pushes back on the water, simultaneously keeping the boat from capsizing and creating another pressure differential, which pushes the boat in the windward direction, allowing the vessel to move forward instead of sideways. Wind direction is an important factor, and that's why sails need to be adjusted depending on the angle of attack. You can't sail directly into the wind, so you angle yourself off the wind and allow the sails to fill. When running downwind, sloops, the most common type of sailboat today, have massive lightweight sails called spinnakers. Tall ships, like those in Pirates of the Caribbean, have the classic square rigging, which allow the ship to run directly downwind. in addition to the triangular staysails and lateens that allow them to sail into the wind. This square rigging was designed to pull ships along the reliable trade wind routes, where the sails would stay the same for days or weeks at a time while these ships crossed oceans. Hull speed is the maximum speed a boat can travel while still running efficiently. When a boat moves through the water, it creates a wave crest along the side of the boat with a trough behind it. As the boat increases speed, the wavelength increases. Once the end of the crest reaches the center of the boat has to start climbing its own crest. And the faster it goes, the larger the crest, so the boat has to do much more work to climb it. One way sailboats can go faster than their hull speed is by using their sails to create lift. Not the kind of lift caused by pressure differentials, but using the sail shape to physically lift the bow of the boat out of the water. Large downwind sails, like spinnakers, are designed to bellow out in front and above the boat to create even more lift. I'm not going to do the math on this because sources are hard to come by, and as someone who can do this in the field, so to speak, I can tell you that it's not an exact science. You do a lot of this by feel. The only reason you'd need to calculate the physics of exact sail adjustments is if you're teaching robots how to sail, which is a thing, but I refuse to acknowledge it further out of anti-autonomous sailboat bigotry. Another way to increase hull speed is increasing the boat's length at the waterline. You can weigh your boat down more, though this also creates more drag. With sailboats, you can heel over, which increases the length at the waterline without increasing the weight. Some boats even have a sloped stern, which can add a few feet to the waterline without increasing deck length. A third way to increase hull speed is adding a bulb at the front of the bow. This creates its own wave, and the bulb's size is calculated such that the bulb's trough lines up with the crest of the hull, decreasing the amplitude of the crest so that it's not as much of a climb and the boat can go faster. So, though we're taking it with a grain of salt and know that it's only theoretical, the equation for hull speed is 1.34 times the square root of the boat's length at the waterline. If the Black Pearl's length at the waterline is 160 feet, being generous, her theoretical hull speed is 16.95 knots, 19.505 miles per hour, or 8.72 meters per second. Also, fun fact, don't look it up, the Black Pearl has no drag in the water. That's why the Pearl is nigh uncatchable. She has no drag in the water because Jack sold his soul in exchange for Davy Jones raising her from the depths. This ship is undead and has been resurrected more times than Jesus, so why would her hull have any drag? That's the real reason why the Royal Navy and the East India Trading Company are angry at the pirates. They're soups jealous. All the colonization and slave trading in the world can't buy hulls with negligible friction, and the way they handle it is about in line with how any dictatorship would handle a populace they can't control. This shot of her hull, all covered in barnacles, is capitalist propaganda by Disney and the East India Company, shoehorned into a socialist film. The points of sail are nearly unlimited, and that's why sails are adjustable. But we are going to focus on 4. Close-hauled is as far upwind as a sailboat can point. On most boats, that means that if the bow is pointing towards 12 o'clock, the wind is coming in at 1 o'clock or 1:30. Beam reach is when the wind is perpendicular to the boat, so the wind is coming in at 3 o'clock. Broad reach is when the wind is off the stern quarter, or around 4:30. And a downwind run, which on sloops like the boat in this diagram usually means that there's still a bit of an angle to the wind. But when looking at tall ships, for calculation's sake, we're going to say that the wind is coming from directly behind the ship. Let's look at a real tall ship's calculations. The Lady Washington, our state ship, has a mass of 100,589 kilograms and a length at the waterline of 72 feet, or 22 meters. Giving her a theoretical hull speed of 11.455 knots, or 5.893 meters per second. She is a much smaller ship than the Pearl, being about 44% of the undead ship's length and a quarter of her mass. Because of this size discrepancy making it hard to compare Lady Washington with the Black Pearl, at the end of this segment I'm going to share how a lack of drag would affect our state ship's velocity and acceleration calculations. Applying the concept of drag, when the Lady Washington has a velocity of 0.01 meters per second, her drag has a force of 207.9 newtons. But when she is up to hull speed, she has a drag force of 122,515.5 newtons. And while the exact number varies based on the wind speed, the acceleration is relatively high, more than 1 meter per second in some of my calculations, when the ship's velocity is low, but at 0 meters per second or lower as the drag force matches and possibly surpasses the forces propelling the ship forward. This is why Davy Jones gave the resurrected Pearl no hull drag, specifically so that I don't have to factor it into the myriad of calculations I will be doing with her later. Here's a chart illustrating the inverse correlation between the drag force and the acceleration. And here's another chart showing the theoretical maximum boat speeds under different wind velocities. I admit my calculations may be missing some details, since there are many factors at work on a sailboat that would increase or decrease the variables that factor into change in speed. That being said, I have calculated that the Lady Washington requires a wind speed of at least 16.3 meters per second, 36.7 miles per hour, or 31.9 knots to reach and maintain a hull speed of 5.893 meters per second. Decrease the wind speed to even 16 meters per second, and Lady Washington can't reach hull speed. Decrease the wind speed to 10 meters per second, and Lady Washington can only get to 2.25 meters per second. Take this all with a grain of salt. I bet there is some way for her to reach hull speed without gale force winds, but I can't hack it mathematically. If the Lady Washington, like the Black Pearl, had no hull drag, a wind of 10 meters per second, or 22.4 miles per hour, would allow her to reach hull speed in 12.8 seconds, covering only 37.7 meters to do so. Remember, with normal hull drag, she could only reach a velocity of around 2 meters per second under the same conditions. Even with wind of only 5 meters per second, or 11.2 miles per hour, where normally she could hardly reach 1 meter per second of net speed, without drag, she could reach hull speed in 50.8 seconds, covering 149.7 meters of water to do so. Now, with an increased appreciation for Davy Jones's gift of a lack of drag, let's return our attention to the Black Pearl to see how she handles different points of sail. When running directly downwind, the wind blows into the square-rigged sails directly from behind. One would assume. I don't know how to sail tall ships. I'm going based on the knowledge that square-rigged sails were designed for running for weeks at a time with the trade winds, and if you angle off the wind, you'd eventually leave the trade wind latitudes. I digress. On the Black Pearl, the square rigging in use, going directly downwind, have a total surface area of just under 395 meters squared. The bottom sail on the foremast is out of commission because it would be shadowed by the bottom sail on the mainmast. The pressure difference on the sails is between the wind blowing directly onto the sails and the wind blowing past the sails. When true wind is blowing 10 meters per second, or 22.4 miles per hour, there is a pressure difference of 57.4 pascals. This adds 22,678 newtons of lifting force, creating a net force on the ship of 45,356 newtons and 0.1116 meters per second squared of acceleration, allowing the ship to reach hull speed in 1 minute and 18 seconds, traveling 341 meters over the water. For both beam reach and close haul, the square rigging on tall ships is useless, and the Pearl has to use her staysails and lateen to cut through the wind. These have a total surface area of just under 399 meters squared. The pressure difference with the sails cutting through 10 meter per second wind is also 57.4 pascals, giving the Pearl 22,881 newtons of lifting force. This comes to a net force of 45,763 newtons and an acceleration of 0.1126 meters per second squared, allowing the ship to reach hull speed in 1 minute and 17 seconds, covering 338 meters of water to do so. Though the numbers may make it seem like it's similar to sailing downwind, the big difference here is the fact that when the wind pushes on the sail one way, the water is pushing the other way, which keeps the ship going straight instead of sideways. There's also something called apparent wind, which is the relative wind felt by the boat and its passengers due to the forward motion. For example, when sailing in a beam reach with 5 knots of true wind, as pictured here, and the boat's velocity is, for mathematic simplicity, also 5 knots, the apparent wind is 7.07 knots, 45 degrees off the bow, rather than directly perpendicular to the boat. So the sails should be sheeted in accordingly, and the boat can then go faster than true wind. The most common sail setup to see in the Pirates films is a broad reach. This is when the wind is coming off the stern quarter and hits the sails at an angle that allows all sails to be up. This happens to be the coolest look, so it makes one wonder. Perhaps there's some oracular wind god in the Pirates of the Caribbean universe who lives for the drama. Considering the loose use of Greek mythology in these films, my money is on the bisexual icon Zephyrus. He sees something interesting coming and pushes the wind around behind them so it can happen under aesthetically pleasing sail power. The broad reach also gives a total sail area of a whopping 868 meters squared. The pressure difference with a 10 meter per second wind is the same at 57 pascals, adding a lifting force of 49,827 newtons. This creates a net force of 99,654 newtons and an acceleration of 0.2452 meters per second squared, allowing the ship to reach hull speed in 35.6 seconds, crossing 155 meters of water in the process. So which comic book superhuman would the Black Pearl be? Well, someone better versed in comic book characters might have a different idea, but I'm thinking the Black Pearl is a lot like Jim Corrigan. Much like the Pearl, Jim also has a sordid history pre-death as a cop, and was then resurrected to be the host of The Spectre, who's the, quote, spirit of God's vengeance, unquote, according to CBR.com. So, an angel. I wouldn't go that far with the Pearl, but there was a decade where she could sail with the gnarliest sails, because the nameless Aztec gods placed a curse on some gold that was supposed to affect the mortals who take the gold, but somehow affects the whole ship for some likely god-meddling reason. Anyways, the Pearl has the vibes of an undead guy being forced into a situationship with a god's higher purpose. All's I'm saying. Let's take a sec to talk about square rigging. These sails are limited to an angle of up to 60 degrees off the wind. The absolute highest angle I could find was 80 degrees, which is insane. But all of that data is with more modern ships, so I'm going to limit the Pirates of the Caribbean ships to 45 degrees off the wind. So look at this bullshit. These motherfuckers are sailing directly at each other with all their square sails down. Based on the angles of the sails, these are the directions the external forces propelling the ships are coming from. Yeah, you could argue that that's what makes these ships supercrafts, but that's boring. Screw Occam's razor. Let's get into this shit. Am I crazy? Absolutely. Am I embracing it? Pfft, no, what are you talking about? I think that in addition to wind, the Pirates of the Caribbean universe has another natural force, strong enough to propel ships. The epic music of Klaus Badelt and arrangement of Hans Zimmer. Doesn't that get you pumped up? I propose that music is a natural feature of the environment in the Pirates of the Caribbean cinematic universe, like wind, possibly brought about by the structures of the molecules in the atmosphere. Impossible for us to test, and impossible to prove wrong. Starting here at an initial velocity of half hull speed of 4.37 meters per second based on the length of the wave along the hull, the Pearl seems to move a very roughly estimated 200 meters to reach a final velocity of 5.81 meters per second. The calculated acceleration for this time is 0.036648 meters per second squared, and the time it takes is 39.3 seconds. The sound force calculated to be pushing on the sails is 14,894 newtons, with a sound intensity of 87.4 watts per meter squared. That translates to 139.4 decibels, which is approximately the sound of a jet engine taking off. For reference, exposure to 130 decibels of sound would cause instant damage to our eardrums. The maximum energy a normal human eardrum can withstand in 39.3 seconds is 0.0393 joules, with an intensity of 10 watts per square meter. The energy on the eardrums in this scene over the 40-second period required for the Pearl to get up to speed is 0.34 joules, and no one seems bothered by the noise. No one seems bothered by the sound of any explosions in these movies, which, I think, proves my point. Look at this. Yeah, he's in shock, but I have experience with both cannons and guns, and in addition to knowing that a single gunshot is about 160 decibels, I can tell you anecdotally that none of his cadre would be able to hear his little whispered mantra because their tympanic membranes would be destroyed. Their ability to hear him is a testament to the fact that they have naturally much stronger eardrums than us. Let's say their tympanic membrane can withstand 0.5 joules of energy in a 40-second period. That means their ears can tolerate a sound intensity of 125 watts per meter squared, which is 115 more than we can. The fact that the ships in the Pirates of the Caribbean cinematic universe can move with the sound waves of the diegetic music makes me open to the idea that Davy Jones, taking up so much space on his ship with a pipe organ, is actually quite practical. The sound waves he generates playing his obsessive octopodic oratorio make their way out to the rigging and give the Dutchman an extra boost. Will better learn to play the piano or they'll be in for a world of boredom if they ever get stuck in the doldrums, when the wind and music dies. I hope he got some piano workbooks on his one day ashore, because 10 years of plinking it out with no instruction does not sound fun. Anyways, thanks for watching Boat Physics. I hope it was simultaneously informative and superfluous.